How's it going? Anybody having any trouble with anything? My math lab, everybody's created an account, I hope. So if you haven't done so, go watch the previous videos from last week and register, create an account, get started on that homework. Um, Make sure you log into Canvas at least once so that I can know that you're active and you're pursuing this class. If you haven't done those two things yet, then I don't know that you're actively pursuing this class, so I might drop you. So if you're out there, either here now or later watching on YouTube, you need to create an account with my math lab and you need to log into Canvas, otherwise I'm going to drop you. Okay, send me an email if you're having trouble with anything. Okay. Any questions from 5.1? Did anybody have any trouble with anything in the homework? No questions, no problems, no issues? No. Okay, well, I'll move on then. So section 5.2, the addition rule and complements. Okay, so in this section we're going to learn about how to use the addition rule for disjoint events. So of course we're going to learn what disjoint events are. We're going to use the general addition rule. And, well, in my opinion, I don't think we should have two distinct rules. I think the general rule is the only we should teach, but it's the way the textbook has it, so we're going to do it that way. And then we're going to explore the probability of an event using the complement rule. So again, explore what that means, the complement of an event. Okay, so the addition rule. The addition rule and complement. So two events are disjoint if they have no events in common, right? No outcomes in common. Another name for disjoint events is mutually exclusive events. Okay, so we have an experiment, right? There are outcomes that happen from that experiment. When we list all those outcomes, we call it the sample space. Each individual one of those outcomes are simple events, but then we can create more complicated compound events that come from those. So I know that that's not the greatest explanation, so let's go into an example. So let's say we have this example. We have 10 little ping pong balls numbered from 0 through 9, right? So starting with 1, of course, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and then the 0 makes it 10. So there are 10 individual little numbers. Think about 10 individual little ping pong balls. Each one of them has a number. And maybe they're put into a giant thing and they're circulated, you know, like bingo or something. And then you're going to reach in there and you're going to grab one individual little ball, and that'll be the winner, right? You reach in there and you pull it out and you go, number 3. Who has number 3? Number 3 is the winner. Okay, so the experiment is to select one little ball from the 10, right? So that's our experiment. Okay, let's write in the technology, these things here. So the experiment is to randomly select one number. One number from 0, 1, 2, 3, up to 9. Okay, so there's our experiment. Our sample space, well, you know, notation is one of the big issues in statistics. There's lots of ways to do things. So just to, I think for what I think is the sake of clarity, I'm going to draw them like little ping pong balls. There's the 0, there's the 1, there's the 2, there's the 3, there's the 4, there's the 5, there's the 6, there's the 7, there's an 8, and there's a 9. Right? Here's my sample space, all possible outcomes. Of course, we could also write it down by just writing the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, like this. Okay. Either way you do it is fine. Okay, so we have our entire sample space. Each one of these little possible outcomes is a simple event, which we usually denote with a lowercase e. We can say e sub 1, the first simple event, is that we get a 0. The second simple event is that we get a 1. Well, it would look even nicer if these things matched, but they don't have to match. I could put them in any order I want. The third simple event is that we get a 7. The fourth simple event is that we get a 9. The fifth simple event is that we get a 3, right? And as long as I just really use them all exactly once, I could label them in any way I want. However, math people, we like order, so we often like to write things in a way that they match. So the most popular way to do this would probably be to just say that the first simple event is that it's a 1, the second simple event is that it's a 2, the third simple event that it's a 3, the fourth simple event that it's a 4, the fifth simple event that it's a 5, and so on and so forth, kind of matching. And then of course the 0, we'd have to put that it's the e sub 0 simple event and that it's 0. Okay, so if we use this kind of notation where we've identified all the simple events, I'll call these, let's label them simple events. Good. So since I've identified all my simple events, I can just list my sample space now as e sub 0, e sub 1, e sub 2, right, dot, 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 all the way out to e sub 9. There's my sample space identifying all my simple events. Okay, but now that I have simple events, I can identify compound events. And so compound events are more complicated events that group up these simple events. So here is some examples of what compound events could be. Here's compound event. Event. So we have event E. And event E is made up of these simple things. Either the 0 ping pong ball is selected, or the 1 ping pong ball, or the number 2 ping pong ball is selected. Right? And here's another compound event F, which is that either the little ping pong ball with an 8 is selected, or the little ping pong ball with a 9 is selected. Right? So these are two compound events that are really made up of a combination of simple events. Right? Another way to write this F1 would be to say that capital F is also equal to simple event E sub 8 and E sub 9, right? Based on the way we describe these things over here. Right? But we want to create the notation that best fits the particular word problem. And sometimes doing really complicated notation for a really simple problem, it's kind of an overkill. But in more complicated situations, we might need the more sophisticated notation to help us express our ideas. Right? So in this case, it's probably a bit of an overkill to go through the process of identifying all the simple events this way and then listing the compound event as the combination of the simple events. But it's good to practice them with the simple ones so that if we need it in a more complicated setting, then we have that notation already in our back pocket to implement it. Okay, so a compound event might have a unifying theme to it, a pattern, for example. A compound event might be the even numbers, for example. I could say event capital G, compound event capital G might be the evens. Okay, so then I'm choosing from these. I'm going to pick a little ping pong ball and I want it to be evens. So it might be the 2, the 4, the 6, the 8, right? Or it could be the odds. Capital compound event capital H could be odds. Okay, so I want the 1, the 3, the 5, the 7, the 9. Okay, or maybe compound capital I might be just all numbers that are greater than 5. Greater than 5. Right? So these are all examples of compound events that really are made up by a combination of simple events. So there could be a unifying theme, like all the evens, all the odds, greater than 5, or it could just be some random selection as it's explained here. Compound event E is just the numbers 0, 1, and 2. Compound event F is just 8 and 9, and there might not necessarily be any reason or logic for it. It's just the events as they have been defined. Okay? All right, so imagine that this is the hottest game in Vegas, right? All you're going to do is pick which little ping pong ball is selected. 10 ping pong balls are thrown into a big bin. Each one has these numbers in there. And the dealer, all he's going to do is reach in there, grab one little ping pong ball, and there you go. That's your winner if you get it, okay? So one person E, I don't know, Evan, has placed some money that it's either going to be the 0, the 1, or the 2, right? That's the compound event he's betting will happen. Event F, I don't know, Frank, has chosen to wager money that it's either going to be the 8 or the 9. One of those two is going to happen. Remember, there's only one experiment. You're only going to pick one number. So the dealer is going to reach in there and pull out a number, and if it's either the 8 or the 9, then F will win. Sorry. If it's either the 0, the 1, or the 2, then E will win. And if it's not none of those, it's one of these other numbers, then neither one of these two events will occur, which means both of these people will lose their wagers. Good? Good. Stop me if you have any issues. Okay, so a Venn diagram is a very classic way of expressing these kinds of things. A Venn diagram is made up of a giant rectangle that represents the sample space. Inside the sample space will be all simple events, all possible simple events, and then you grab all possible simple events and then you group them up in circles to identify compound events, right? Such as this. So of course we see the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? All possible simple events are inside the giant rectangle, right? And then we see these little circles that are again identifying which of the simple events make up that compound event. Good? Okay, so all this was to highlight what a disjoint, what it looks like when we have two disjoint events. Two disjoint events is when two events have no shared simple events in common, right? See, they don't share anything in common. Therefore, these two are disjoint, right? Or mutually exclusive. There's no way that both of these events can happen at the same time because they don't have any numbers in common. If they had both bet on the number 2, right? If there's also a 2 in here, for example, then there would exist the possibility that the dealer selects 2 and then they're both winners, right? And in a case like that, this would no longer be disjoint. Okay, but they don't have any numbers in common, so that's why they're disjoint. Any questions? No? Okay, so let's back to the same diagram. Let's figure out some of these probabilities and adopt some of that notation from last time. Okay, so to find the probability that event capital E happens, remember a giant P with parentheses, and then whatever's in here is the event for which we want to find the probability, right? This giant P represents probability. Okay, so the probability of event E, well, we can approach this by the classical method, which means we're going to count things. This is going to be equal to the number of ways that event E can happen, divided by the number of simple events in our sample space, the number of outcomes in our sample space. Good. So the number of ways that E can happen, well, I can just count things. Here they are. There's 1, 2, 3. there are 3 ways in which they can happen. So when I put a 3 here, don't confuse the 3, meaning that there are 3 ways this can happen, from the number 3, meaning the little ball that has a 3 in it, right? So this 3, I'll put it in red here, this 3 comes from the fact that it could be the 0, or it could be the 1, or it could be the 2. Okay. And then we divide that by the number of values in our sample space, and of which there are 10. There are 10 options that could have occurred, right? 10 outcomes in our sample space. When we divide this, we get 0.30, which translates into a 30% chance. Good. Questions, 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 questions. Okay, let's find the probability of event F. Probability that event F will happen, right? If this is the hottest game in Vegas, that means that Frank put some money down that the dealer was going to either select the little ping pong ball with an 8 or the one with a 9. So what are the odds that Frank wins? That'll be the number of ways in which Frank can win divided by our sample space. Okay. So the number of the ways that that Frank can win, there's 2 ways that Frank can win. 2. Right? And again, that 2 right there is referring to the fact that it could be the little 8 that gets selected or the little 9. Okay. And then divided by the number of values in our sample space, again, there's 10. That translates into 0.20, which is 20%. Good. Any questions, any questions, any questions, any questions? Okay, so now let's think about this OR statement. Probability that E or F happens. E or F. Probability of E or F, right? So maybe they're friends, they're joining forces. When one wins, the other one wins too, right? Maybe they're technically playing as 2 separate people, but you know, they're best friends and they're just kind of sharing their money. It doesn't really matter. So, what did he say his name? E, whoever he was, Evan, Elf, whatever. E is just as happy when Frank wins, and back and forth. So maybe we're just trying to figure that probability that one or the other wins. Probability that that E or F happens. Okay, so this is going to be the same notation as before. N of E or F, the number of ways that E or F can occur, divided by the number of possibilities in our sample space. And so now we just count things. So there's 1, 2, 3, 4, 5. There are 5 ways in which E or F can happen. So this 5, again, refers to either the 0 or the 1 or the 2 or the 8 or the 9, right? Those are all the ways in which E or F could happen. And then we divide it by the values in our sample space, which is going to be 10. And so that turns into 0.50, which is the same thing as 50%. Good. So uniting the work we've done here, from here we got that the probability of event E is equal to 30%. And from here we got the probability that event F happens is equal to 20%. And from up here we got that the probability that event E or event F happens is equal to 50%. And so you might see where we're driving at. This is 30%, this is 20%, one or the other. Well, looks like all I did was add them. And that's right, that's what we're driving to. when the two events are disjoint, and it's important to note that this rule is only valid as long as these two events are disjoint. They don't have anything in common. If event E and event F are disjoint, then we can just add them, right? So when I was trying to figure out this probability of event E or F, if I knew that rule in advance, then I could have saved myself some work and said, because events E and F are, are disjoint. Because they're disjoint, that means that the probability of E or F is equal to the probability of E plus the probability of F. Right, we get to add them together. The probability of E we already knew was 30%. I'll put it as 0.30. Plus the probability of F, we discovered that was 20%. So we can just bring them together and say that the probability of E or F is equal to 50%. Good. Any questions at all? No? No questions, no questions, no questions? No? These rules are going to get pretty complicated and messy, so if you have issues, it's important to clear them out now. No? No? Okay, let's see what the author wrote for this. Same thing, I'm sure. So we have our Venn diagram. It's the same question, it's just what the author wrote as a solution. Make sure they match. So the probability of E is equal to the number of ways that event E can occur. We said that was 3, divided by the number of values in our sample space, which we said was 10. So the probability of E is 0.3, which is the 30%. Probability of F is the number of ways that F can happen divided by the number of values in our sample space, which we said there are 2 of them, 2 out of 10, or 0.2. Good. And then we have an option, right? In this case, we have choices. When we want to find the probability of E or F, it's the number of ways that E or F can happen. So we can count things. This 5 right here comes from the fact that I counted 1, 2, 3, 4, 5, right? This 5 is the 0, the 1, the 2, the 8, or the 9, right? That's why there's 5 of them. There are 5 ways that event E or event F can happen, and they're disjoint. They don't have anything in common. So that's why we get 5 out of 10, which is 50%. Right? So in this case, we have the freedom, the luxury of choice, because we could count, and it's pretty easy to count. But it's important to note that the other way to answer this is to just add these two probabilities. And in some questions, you're not going to have the freedom to be able to count from a Venn diagram, because the word problem might be so complicated, there wouldn't be a Venn diagram, or it might be hard to draw one. So we have to be aware of this probability rule so that we can use it and apply it when we need it. Questions? Okay, so here's the general rule then, the addition rule for disjoint events. If E and F are disjoint, so that's important to have, or mutually exclusive, then it's true that the probability of E or F is equal to the probability of E plus the probability of F. Good. Good. Sort of an extension to this, a natural extension to this, would be to break it down into the classical probability description. So the probability of E or F is also equal to the number of ways that E can happen divided by the number of values in our sample space plus the number of values in F divided by the number of values in our sample space. Right? So that's what these are. Or, okay, well, they have the same denominator. We can just bring these two happy fractions together. And another way of saying this is that the probability of E or F is equal to the number of values in E or F, divided by the number of values in our sample space. Right, so all these things are true. Good. Any questions? We can extend that rule out to several events as long as they're all disjoint. So the addition rule for disjoint events can be extended to more than 2 disjoint events. So if we have a whole string of events, event E, event F, event G, event H, event I, event Q, right? So we have all these events and they're all disjoint. They don't share any numbers in common. So for example, instead of just having 10 little ping pong balls, what if we had 1,000 ping pong balls, right? And then lots of people can bet. But let's say that the casino had this rule where they just didn't want anybody to possibly share the winnings, right? Only one person can select a number and that's your number. And maybe you can buy more than one number. So I decide I'm going to buy the number 73 and I'm going to buy the number 18, right? Me. Event E is going to be 73 and 18. Those are the ones I want, right? And then my friend chooses the number 312. That's their favorite number. And then also the number 909 and also the number 101. There you go. My friend bet on 3 numbers. I only bet on 2. And then another friend, H bet on the number 1. Thought that's a lucky number. And the number 7. Number 7. Why not? There you go. So there's 3 different people. These are 3 different events, and they're all disjoint. They don't have anything in common. And we could just keep going. Maybe another friend, friend G, only bet on one number, the number 8. The lucky number 8. Okay, and we could keep going. And as long as all of these events are disjoint, they don't have any numbers in common, then the probability of E or F or H or G is going to be equal to adding up the individual probabilities. Any questions?
What do you mean by it's going to be equal to the probabilities, or to each probability?
The sum of each probability. Right, so okay, so I was just doing kind of a half thought here. Let's finish it up. So in this case, I've extended the experiment. The experiment is to select one number, right, little ping pong balls, from 0 through 1, 2, 3, ... all the way out to 999, right? Therefore, there are 1,000 little balls in there, right? 1, 2, 3, up to 999, and then the 0 counts as the 1,000th ball, right? So what are the odds that a probability that event E happens by itself? Well, it's the number of ways that event E can occur divided by the number of values in our sample space. And there are 2 ways that I could win. I'd put money down on 2 of those numbers. So that would be 2 out of 1,000 in this case. Good. And so as a decimal, this turns into 0.002. And then as a percent, that turns into 0.2%. So there's a pretty small chance, right? There's 1,000 numbers in there. What are the odds that only one of the 2 that I put money on is the winner? There's a pretty small chance. Good. Okay, so then my friend, probability that F happens, well, we see the pattern that happens here, so I'm just going to jump to the punchline here. The probability that F happens is going to be equal to 3 out of 1,000. That's going to be 0.003, which is 0.3%. Good. Probability that event H happens is 2 out of 1,000. which is going to be 0.2% again. And finally, the probability that G happens, according to this little thing, probability that G happens is 0.1%, right? 1 out of 1,000. So now the combination of what is the probability that E or F or H or G, because these are all mutually exclusive, they don't have anything in common, then our rule says that this probability can be found by finding the individual probabilities and then adding them together. It's equal to the sum of these four numbers. Good. So we already found those individually. We said this one was 0.002. This one is 0.003. This one is, oops, did I put them in order? F is 3, yeah, 0.002 and 0.001. Good. So they add up to 2, 5, 7, 8, 0.008, or 0.8% chance. 0.8% chance. So the probability that one or the other wins, right, E or F or H or G, right, can more than one of these happen at the same time? Well, no, because we're only picking one little ball, so it's either the number 7 or the number 908. There's no way that both F and G at the same time are winners. So it's either going to be one of these guys, E or F or G or H, or nobody. Maybe none of these guys win. So the probability of the or statement, the probability of one or the other, in this case, is the sum of the individual probabilities, because they're all disjoint. Did that answer your question? Does that make sense?
Yes, thank you.
Okay, good. And here's another example, extending it a little bit to multiple disjoint events. So here's a way to classify housing in terms of rooms in the house. So, you're going to have to add a little bit of clarity, to really specify what defines a room and what doesn't define a room, right? Does a room have to have full enclosures? What if there's only 3 walls? Does that count as a room? Okay. What if it does have 4 walls, but it doesn't have any windows? Is that a room? Like, does a closet count as a room? Right? So you have to be kind of clear on what you define as a room. I believe most housing codes count a room as a place, a space that can be fully enclosed once you close doors and windows, and must have at least one door and must have at least one window in order for it to be considered a room in your house. There's also perhaps some size measurement, square feet requirements, right? If it's like a closet, like a tiny little closet, you can barely step in there and barely close the door, and maybe it does happen to have a tiny little window. Does that count as a room? Okay, but so you're gonna have to like really get into the fine details of what is a room, but what isn't a room. But let's ignore that for a minute and just think about what rooms are. Okay, so here is a table that describes the housing units in this country. So the probability model to the right shows the distribution of number of rooms and housing units in the United States. So this is saying, let's just jump to this one, for example. This one is, oops, that's not what I wanted to do. Do highlighter. This one, for example, is saying that 12.2% of all housing units in America. This one is saying that 12.2% of all housing units in America have 7 rooms, right? So maybe a kitchen, a living room, maybe a dining room. A lot of places still have a formal dining room, and a bedroom, bathroom, another bedroom, another bathroom. Okay, so that might be like a 2-bedroom, 2-bathroom house, perhaps. right? But again, you're gonna have to be very specific on what you mean by a room. But okay, we have some loose idea of what that means. 12% of all housing units have 7 rooms. 18.9% of all housing units in America have 6 rooms. Is it possible that one single house has both 7 rooms, but it also only has 4 rooms? No, right? I mean, it depends on, you have to be very clear on how you define rooms, right? Really, like, really hash it out, really, really, really specify what constitutes a room. But once you look at one house, you randomly select one house and you examine it, then it should only qualify as one of these things. It either has 7 rooms in it, or it has 4 rooms in it, or it has something else, but it can't have both 7 and at the same time 4. Good. Total rooms. 4 total rooms, but also at the same time it has 7 total rooms. Yeah, that doesn't make sense. So all of these have to be disjoint events, right? Good. So some places only have 1 room, right? That's pretty small. That's not even a studio, right? Because most studios at least have like the bathroom separated from the rest of the house. So I would say 2 rooms is what we consider a studio. I'm not really sure. I mean, a 1 room house. So bathroom, kitchen, living room, dining room, bedrooms, just 1 room. So that's kind of tough, right? So maybe it's a house that doesn't have any bathrooms. I guess that kind of exists. Um, there's like commonly shared bathrooms, so it could be kind of something kind of like dorm rooms kind of thing, where you have your space and your room, your giant room where you have kitchen and living room and bedroom, and maybe it just doesn't have a bathroom. And to go to the bathroom, you have to go outside of your apartment and go into, down the hall. There's a big giant common bathroom for everyone. I guess that could be what this is. Or maybe you do have sort of a bathroom space within one big room, right? I'm not really sure what this would be. Maybe it could be like a giant loft, maybe like a giant loft where they don't even have. I don't know. Any rate, so houses either have 1 room, 2 rooms, 3 rooms, 4 rooms, 5 rooms, 6 rooms, 7 rooms, 8 rooms, and then after that we just classify them as 9 or more. This is pretty common, right? Because otherwise we're just going to go on forever. 10 rooms, 11 rooms, 12 rooms, 13 rooms. And in fact, there's so few housing units that have more than 9 that it just makes more sense to just group them up, right? Lump them up into this. Right? Also, it makes no sense to have 0 rooms. You can't have a house with 0 rooms, and then technically it's no longer a house, right? No longer a housing unit. Good, 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 good. Okay, so verify that this is a probability model. How do we verify that? A proper probability distribution model has a few characteristics, right? All possible events must be listed. So if we're going to randomly select one house in the United States and classify how many rooms that house has, then all possible outcomes must be listed. So 1, 2, 3, 4, 5, 6, 7, 8, and then 9 or more includes all possible outcomes, right? There's no way that it will have any other number. And of course, again, we have to be very specific on what we identify as a room, and we're specifying that we can't have fractional rooms, right? You can't have a house that has 2.5 rooms, or 4.5 rooms, 4.27 rooms. In some contexts, you might consider that. For example, bathrooms are often classified with fractions as 1.5 bathrooms, right? To really further specify that one bathroom is complete. It's got a toilet, it's got a shower, and it's got a tub, and right, it's a complete bathroom. Whereas if they call it a 0.75 bathroom, a 3/4 of a bathroom, it means it has a shower, but it doesn't have a tub. And if it's a half a bathroom, it means it just has a toilet, but it does not have a shower or a tub. Right? Anyway, so in some context, you might have fractional or decimal values. But in this context, we're eliminating all decimal values, and we're just simply identifying rooms. Okay, so all possible outcomes are listed. And then in order for it to be a proper probability distribution, it must be true that each one of these probabilities is a value between 0 and 1 inclusive of the endpoints. And that's also true here. Remember that in statistics, we can't have a number that's greater than 1, because that would mean it's greater than 100%. And that doesn't have a, that's not valid in this area of math. And also we can't have a negative, because that also doesn't make any sense here. We can't have a negative probability. Okay, so it satisfies that rule. Each one of these probabilities is between 0 and 1 inclusive. So that's rule number 1. But rule number 1, for it to be a proper probability distribution, I'll put each probability is between 0 and 1 inclusive. Right? That inclusive means that 0, the actual 0 is allowed, and 1, the actual number 1 is allowed. If it didn't put inclusive, it would mean that we could get infinitely close to 0, infinitely close to 1, but never actually include the endpoints. Okay. Another notation for this, we could say probability of any event, right? Remember, this giant P always means probability in statistics. Probability of any event is less than or equal to 1, greater than or equal to 0. Right? That's what this is saying. Good. The other requirement for this to be a proper probability distribution is that the sum of all these probabilities better add up to 1. So we need 0.010 plus 0.032 plus 0.093 plus 0.176 plus ... all of them, right? So we add all of these up, and if we add all of them up, they better add up to 1, right? That's what we need for the second condition of a proper probability distribution. So if we get our calculator out and add them all, we'll see that they do add up to 1. Any questions about the two conditions for a proper probability model? We're good? Okay, so let's see, the author does that. Okay, so part B, what is the probability that a randomly selected housing unit has 2 or 3 rooms? 2 or 3 rooms. Okay, so this is an example where we don't have the benefit of a Venn diagram. We can't just count our way to the answer like we did before. Here we have to take advantage of our addition rule for probabilities. So the probability that we have 2 or 3 rooms, so 2 or 3, right? And writing them out, because I don't want the number 2 to get confused with something else. So this is equal to the probability that we have a house with 2 rooms plus the probability that we have a house with 3 rooms. Good. And again, this is true as long as these two events are disjoint, right? And they are disjoint in this case. Disjoint events. Good. Okay, so now the probability that we have 2 rooms, well, that's just provided right here. This is equal to 0.032 plus the probability that we have 3 rooms is 0.093. Good. And they add up to 0.125, I believe. Good. Or 12.5%. Good. Questions? No? Okay. So remember to start practicing the notation. When the test comes around, I don't want to see just the answer 12.5. If this was the question and I gave you this table, I expect to see this work written down. The probability of 2 or 3, make sure you write down the or in there, is equal to the probability of 2 plus the probability of 3. And then you can just grab this from the table. There's nothing else that needs to be shown here. And then you get to this, right? But if someone just turns in the number 12.5, that's not going to get you full credit, right? I need to see full mathematical statements written down. So make sure you practice that as you do your homework. Okay. All right. And then here's a little thing what the author wrote, and it matches what we did.
Sorry, quick question.
Yes.
For the test, the way our test is going to be, it's going to be separate from our homework, right? Like in the sense of how you're saying we have to state the whole problem, like from P of 2 or 3. Like our test will be completely different how we've been doing homework from the Pearson lab, right?
I want to say yes and no. Here, let me explain what I mean by that. The Pearson does ask you to do things in full, complete sentences. However, they kind of help you along that process in the way it's formatted. So it's kind of like little training wheels where a lot of the stuff is fill in the blank. Like if this was a homework question presented by Pearson, they might have a little drop-down menu for you to select the 2 here, a little drop-down menu to select the 3 there, and then they ask you to write it down. Now they might ask you got to follow the instructions. Sometimes they ask you to just present the final answer as a decimal. Sometimes they ask you to convert it as a percentage. So there's that. Also, of course, when you do the homework through Pearson, they're not asking you to turn in the work. They just want you to present the final answer in a sort of a full sentence format, and again, they might kind of help you along with that. So I wouldn't say that it's completely different. It's just that when the test comes along, the way it's going to be done is that it's going to be through Canvas. The question will be presented. So like maybe this question is presented to you on Canvas, and then you have to do the work on your own piece of paper. Get your own sheet of paper, you write it all out, show all the details, and it's that paper that you're going to take pictures of and turn into me. So ultimately, it'll be it'll simulate the in-class environment where you write it all out and then you give it to me.
That makes a lot more sense. Thank you.
Okay, good. Anybody else? Questions on anything? No? So as you do your homework on Pearson, again, I would recommend that you have your own notebook or binder or something, and you work it all out. If there's any calculations that need to be done, any formulas that need to be used, work it all out nice and neat, organized. When you get to your answer, then you submit it on Canvas. I'm sorry, you submit it on MyStatLab, and hopefully it's right. And but you want to save that work, right? Because when the test comes along, I don't want just a bunch of answers. I want you to show me that that's the answer, right? The exams are not there for you to tell me what the answers are. The exams are there for you to prove to me, to convince me that that's the answer. I need to be convinced that this is the answer and that it's not, it can't possibly be anything else. Good? So convince me. Show me it has to be this, that the answer has to be this. Good. Okay, here's another example. What is the probability that a randomly selected housing unit has 1 or 2 or 3 rooms? Right? So one randomly selected house in America. What is the probability that it has 1 or 2 or 3 rooms? Well, again, we get to use our addition rule. The probability that it has 1 or 2 or 3 rooms, right? All of these events are disjoint. Disjoint events. They can't happen at the same time. One house is selected, it either has 1 room, or it has 3 rooms, or it has 8 rooms. But it can't have 1 room total and at the same time 8 rooms total. Right? They're disjoint. So according to our addition rule, that means that this is equal to the probability that it's one room plus the probability that it's two rooms plus the probability that it's three rooms. Good. And reading it from our probability distribution table, that's just going to be these three numbers there. The probability that it's got one room is 0.01 plus the probability that it's got two rooms is 0.032 plus the probability that it's got three rooms is 0.093. As percentages, we can convert all these. This would be 1%. This would be 3.2%. Plus, this would be 9.3%. Right, moving the decimal over two spaces. So this would be 12.5 or 13.5. 13.5%. Good. Questions, 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 questions? Okay, 13.5. Moving on. Now let's say we don't necessarily know that events E and F are disjoint. They might be, they might not be. So this is a more generic rule that applies for all situations, which is why I think the rule we just covered shouldn't have been really presented. The general rule encompasses everything. So if I was the author of this textbook, I wouldn't have included the previous rule and just covered this one. This covers everything. Okay? For any two events, E and F, the probability of E or F is equal to the probability of E plus the probability of F minus the probability of E and F, right? And so maybe we should spend some time thinking about what this is, although I think it's kind of intuitive. Probability of E and F means that both event E and event F happen at the same time. If we go back to our ping pong balls, right? Let's say we have the experiment where we're drawing one little ping pong ball, and let's say there's just back to 10 of them. We could have event E where, let's put them in green. Maybe one person bets that it's the number 8, the number 9, and the number 1. Those are the three that event E, person E has selected. And let's say that event F is that they think that 9 will also be the winner. So see how they have something in common? They're both betting on 9, but maybe F is also betting on 2. This must mean that all the other numbers are out here. So 0 is out there, 1, 2, 3 is out there, 4 is out there, 5 is out there, 6 is out there, 7 is out there, and then 8 and 9. Good? Okay, so that encompasses all 10 options. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And now based on this, obviously the probability that event E happens is equal to the number of ways that event E can happen divided by the number of values in our sample space. And so E can happen in 1, 2, or 3 ways. 3 out of 10 ways, or 0.30, or 30%. 30% ways that can happen. And that 3, this 3 right here, this 3 is not the little ball with a 3. People confuse that a lot. This 3 is because of one of these guys. It could be the 1, it could be the 8, or it could be the 9. We're identifying the different ways that event E can happen. Good. Now, event F, the probability that event F happens, that's equal to the number of ways that event F can happen divided by the number of values in our sample space. And event F can happen in one of 2 ways, either the number 9 or the number 2. So there's 2 out of 10 different ways, or 0.20, or 20% chance that it can happen. Good. So that 2 is not referring to the little ball with a 2 on it. This is referring to the fact that it could either be the 9 or the 2. Good. Now this AND statement means that they both happen at the same time. So the probability that E and F happen at the same time is equal to the number of ways that E and F happen at the same time, divided by its sample space. And if we look at it, there's only one way that they both happen at the same time. It's the number 9, right? So it's 1 out of 10. And again, that 1 is not the little ball with a 1 on it. This 1 is representing the number 9, right? That's the only way that both of them are winners at the same time, right? The dealer picks one little ping pong ball, yells out 9. There you go. 9 means that both of them are winners. Good. So that translates into 10%. 0.10, which is equal to 10%. Good. Okay, so now when we're trying to think about the probability of E or F, note that the probability of E or F, okay, well, one thing is we do have the benefit of a Venn diagram. We could count things, so that's good. Probability of E or F is equal to the number of ways that E or F can happen divided by the number of ways in our sample space. So if we have the benefit of counting things, we have 1, 2, 3, 4 ways that that can happen. So this is 4 out of 10. And again, that 4 refers to the numbers 1, 8, 9, and 2. Right? Those are all the ways in which E or F can happen, or both, which then gives you 0.40 or 40%. Right? There's a 40% chance that E or F happens. That has to be my answer. Right? I got that from counting things. Notice that the probability, note, that the probability of E or F is not equal to the probability of E plus the probability of F like it was before. This is not going to be true here, right? Notice that the probability of E is 30%, probability of F is 20%. So in this case, the probability of E or F, according to this rule, would be equal to 50%, and it's not. We already know the answer. The answer is 40%, not 50. Right? So what's wrong, why this doesn't work, is because these two events are not disjoint. They have something in common. Right? They have that 9. So if I just apply this rule, the number 9 is part of this 30%, right? There it is. It was counted here. So the 9, the little ball 9 was part of there. But also the little ball, the 9 ball, was also part of F. It was right here. We counted it there. So the number 9 is being counted twice. That's why it's off. So what we have to do is correct this process by subtracting the E and the F, the probability of E and F. Right? That will correct this problem that we've overcounted. Kind of, maybe, sort of. So if we want to use the general rule, given that they are not disjoint, then this is going to be equal to, let's put it over here, the probability of E or F is equal to the probability of E plus the probability of F minus the probability of E and F. The probability of E was equal to 0.30. The probability of F was equal to 0.20 minus the probability of E and F, which was equal to 0.10. Right? So this will be equal to 40%. Now they match. Right? Here we got it from counting. We just went to our Venn diagram and started counting things. So that's how I counted that there are 4 out of 10 ways that E or F works. Whereas here, I'm getting it by looking at my probabilities. Probability of event E is 30%, probability of event F is 20%, probability of E and F is equal to 10%, and that's how I get this. Good. Again, the reason we subtract is because the number 9 is being counted here. It's part of this probability of E. There's a 9 in there. Right? There's a 1 and there's an 8 as well, but there's a 9 in there. There's also a 9 in here. So we've overcounted it. So we need to correct it. We need to subtract the overlap, and the overlap is exactly the 9. Good. So we add it twice, we add the 9, we add the 9, so then we subtract it one time. That way, one of them kind of cancels, and then we've counted the 9 exactly once instead of counting it twice. Questions? Questions? No? Kind of, maybe, sort of. Okay, so let's look at another example, same thing. Another example on the general addition rule, but this time let's use dice. Let's get away from this ping pong ball thing. So let's say we're rolling 2 dice, right? They're 2 6-sided fair dice. And let's say that we have a way of identifying die number 1 versus die number 2. So maybe one of them is, blue and the other one is red, for example. Or maybe we toss them one at a time. First we roll die number 1 and then we roll die number 2, right? Or there's any number of ways. Maybe they're in 2 different tables or something. We toss them so that they don't mix with each other and we know which one's which. Or it could be one of those little bobble things, little bobble sphere things that you can like pop, and then the little dice in there flies around until it lands on something. So at any rate, we need to keep clear which is die number 1 and which is die number 2. So if we roll 2 6-sided dice, this right here, this table describes for us all possible outcomes, right? From they're both 1s to this one right here means that the first die was a 4, the second die was a 3, right? So in this notation, we're adopting that the die on the left is the first die and the die on the right is the second die. Good. So this describes all possible outcomes. Each one of these little pairs is a simple event, not just an individual die result, right? So just having this is not a simple event because there's only one die. The experiment is to throw a pair of dice. So each one of these things is a simple event. So 3 and 1, that's a simple event. And 4 and 1, that's a simple event, right? Dot, 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 dot. So all of these are simple events. And how many are there? Let's see, there's 1, 2, 3, 4, 5. There are 6 simple events going this way. And there's 1, 2, 3, 4, 5, 6 simple events going this way. So there's a total of 36. 36 simple events. Good. So if I asked you, what's the probability when a pair of dice are thrown, what's the probability that the first die is a 4 and the second die is a 1, exactly like this, that's just one of the simple events, well, then that's just going to be 1 out of 36, right? Probability that we get simple event number 2, as defined right here, is just going to be equal to 1 out of 36. Right? That's a simple probability to figure out. But life's not that simple. We have more complicated events. Here is event E. Event E, the compound event E, is described as the first die is a 2. Right? So event E, capital E, let's erase this thing. Okay, so we don't want to adopt that notation. We could, but we don't want to. That's just too cumbersome for our needs right now. Okay, so event E is described as the first die is a 2. First die equals a 2. Okay, so if I wanted to list them all, first die is a 2. That's these guys right here. Right? So it's this one. It's the 2 and a 1. And then it's the 2 and a 2. Sure. And then it's the 2 and a 3 right? And then, okay, the other ones. I'd rather just highlight them, see if I can highlight them here. It's this guy, and 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 that guy, right? There are 6 of them. Good. Questions? The number of elements in event E is equal to 6, right? Good. Okay. Event F is the sum of the dice is less than or equal to 5. That's the other compound event. Sum equals less than 5. Oh, I shouldn't say equals them. Sum is less than 5. Less than 5. Another way I could say is that the sum is less than 5, like that. Or another way I can say is that the sum equals, okay, less than 5, sum is, so less than 5 means that 5 is not one of the options, right? Less than 5. So 4 is the smallest one, the biggest one that fits under the statement less than 5. So the sum is 4 or 3 or 2. Well, if you think about it, the smallest the sum could be is 2. So that's it. The sum is 4 or 3 or 2. Good. So event F is made up of this situation, the 1 and the 1, add up to 2. And there's no other way that we can add up to 2, right? So that's it. The other one is that maybe they add up to 3, and there's a couple of ways that can happen. Maybe the first die is a 2, second die is a 1, or the other way around. The first die is a 1, the second die is a 2. Right? That's all the ways in which they can add up to 3. Or maybe they add up to 4. And there's a few ways that can happen. Maybe a 3 and a 1, or a 2 and a 2, or a 1 and a 3. 1 and a 3. I know my drawings are messy, so it's easier to just highlight them up here. So let's use this highlighter. So it could be this one, right? That adds up to 2. It could be this one, that adds up to 3. Could be this one, that one adds up to 3. Could be this one, it adds up to 4. This one adds up to 4, and this one adds up to 4. Right, so this little triangle up here describes event F. Do we have a pink in here? I don't know, salmon looking color? Whatever, close. These guys up here are event F. This little corner, right? And the yellow is all of these guys. This whole column over here is event E. Good. Questions? So here is event E, and we'll just use red. And here is event F. And then, of course, they have something in common. These two outcomes are shared by both events. Okay? If the dice roll up as 2-2, like this, then they satisfy event F. If somebody bet that the sum of the two dice was going to be less than, oh, shoot, or equal to 5. Oh, I don't read. Sorry. The sum is less than or equal to 5, so we got to throw in that 5. Okay, so let's fix this. So the sum is less than or equal to 5. Blame you guys. You didn't say anything? Just let me go on and on and on. So we have to throw in a 5 in there as another option, which means it increases the number of possibilities over here. Right, so then, if I continued with my drawing here of every possible case, let's erase this stuff over here. Okay, so highlighter time. It's going to include these, include these, include these, include these. But now equal to 5 means that we can also consider these cases here, right? So it's a bigger triangle. That's what's happening. So this is event F. All of these guys. Good. And we still have the same event E, which is all of these guys. Good. Okay, but now we have three different outcomes that are shared by both event E and event F. Okay. So event F just got a little bigger because now we can also include the possibility that it's a 4 and a 1, or maybe it's a 3 and a 2, or maybe, right? So there's a few more options. Good. And how many options are there for event F? So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different options. Right? I got lazy and stopped doing the rest of those. So event F has 10 different options. Any questions so far? Good. Okay, so let's find the probability of these guys. So the probability of event E is equal to the number of ways that event E can occur divided by the sample space. And as we counted before, there are 6 ways that event E can happen. 1, 2, 3, 4, 5, 6 different ways. But the first die is a 2. So 6 out of 36, which reduces to 1 out of 6. Good. We can use our calculator to convert that into a decimal, and we're going to get that this is equal to 0.167. Probability that event F happens is equal to the number of ways that event F can happen divided by the number of values in our sample space. As we counted, there are 10 ways that can happen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different ways. So 10 out of 36. And we can reduce that so to 5 out of 18. And, I actually don't know what that is. Let's get our calculator now. There's our calculator. That's 5 divided by 18. Gets us to 2778. So this is 0.2778. Good. Now, if we want to find the probability of E and F, probability of E and F. Can they both happen at the same time? Well, we said that they have some items in common, right? Let's highlight it in a weird color, see if it'll look good. Would green look good? No, that's not gonna look good. How about blue? No, that's not gonna look good. Well, okay, you get the point. No. Anyway, these 3 options here satisfy both, right? So they constitute the statement E and F. So this will be 3 out of 36, and this 3 right here is counting the ways in which both can happen. So it counts the 2 and the 1, like that. And it counts the 2 and the 2, 2 and the 2, and it also counts the 2 and the 3, 2 and the 3, right? So there is 3 ways in which both events can happen at the same time. Good. So then we could reduce that into 112. If we and then we can go over to our calculator and divide. You don't have to reduce it, by the way. You can just write it as 3 divided by 36. And you get 0.0833. Good. Now we're finally ready to do our OR statement. What is the probability of E or F? Well, here we have options. Because we have a nice, pretty diagram showing our entire sample space, then we have some options. We can either count things, right? How many ways are there to do one or the other? Let's count them. N of E or F over N of S. N of S we already know is 36. Now E or F, we're going to come over here and just count things. So this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7, this is 8, 9, 10, 11, 12, 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There are 13 different ways that one or the other, or maybe both, happen at the same time, right? In statistics, this OR statement is inclusive. E or F, or maybe both. Good. So by counting from our sample space, I get that the answer should be 13 out of 36. Good. And then I can go over to my calculator and figure out that 13 out of 36 is clear. 13 divided by 36 is 0.3611. Equals to 0.3611. Good. So that's by counting, by the benefit of just counting them. But now let's use our addition rule, right? This rule right up here to confirm that it continues to work. Good. So the other way to do this would be to say, well, no, what I want to do is the probability of E or F is equal to the probability of E plus the probability of F minus the probability of E and F, right? And we have all three of these pieces right here. Probability of E, now I'm going to leave it as I'm going to use this part of it, where I leave it as a fraction like this. So I'm going to copy them down here. From previous work, I saw that the probability of E is 6 out of 36, plus the probability of F is equal to 10 out of 36, minus the probability of E and F, which is equal to 3 out of 36. Luckily, they all have the same denominator, so I could move this over here and say that this is equal to 6 plus 10 minus 3 out of 36, which gives you 13 out of 36. Same answer as before. Good. Or, keep in mind that there might be a word problem in the future where they don't give you the Venn diagram, they just give you the specific probabilities. So they might say, you can envision a word problem that says, probability of event E is 0.167. Probability of event F is 0.2778. Probability of event E and F is 0.0833. What's the probability of event E or F? Okay, well, probability of event E, they might give you the fraction, they might give you the decimal, so that's equal to 0.167, plus this one is 0.2778, minus this one, which is 0.0833. So we can just type those into our calculator, and we're going to see that that's going to give us approximately equal to this. Approximately. I should put wiggly equal signs, mean that it's an approximation. Right? So I'm just saying it's approximately equal to this result up here. It's It's not going to be exact because we did some rounding here, right? So that's why it won't be the exact answer, but it'll be close enough. Good. So the probability of E or F can be found in one of two ways in this case, because we have the nice Venn diagram, nice diagram to help us figure out the answer. Any questions? No? 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 Notice again that we're doing this thing where we're overcounting when we add the two probabilities, E and F, so then we have to correct it by subtracting some of it. The case where the dice are 2 and a 1, like this one, this case right here, 2 and a 1, this case is part of the F. When I was counting F right here, it's part of those 10. So it's been counted already. And then when we did the probability of E, the 2 and the 1, that was part of the E. It has been counted. So this case has been counted there and there. It's been counted twice. We only wanted to count once. That's why we subtracted once. Does that make sense? Any questions? Okay, so now, this is a relatively simple example, but we want to draw from it is sort of confidence in this formula, because this formula has 4 pieces in it. It has this, 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 and this, right? This equals this combination of 3 things, but in a future, more complicated word problem, they might give you 3 out of 4 of these things and ask you to find the missing one. Right? There could be a word problem that says the probability of E or F is 0.3611. The probability of F is 0.2778. The probability of E is 0.167. What's the probability of E and F? Right? So as long as they give you 3 out of the 4, you should be able to find the missing one. Right? Now, to make things even more complicated, they might not present the problem as straightforward as saying the probability of E or F and the probability of E and F. They might tie some sort of word problem. For example, it might talk about, it might say that event E is the probability that one randomly selected high school student has never passed a statistics class. And event F could be the probability that a randomly selected high school student has a full-time job, before the age of 20, something like that. So we could have an or statement, one or the other. We could have the individual probabilities, and then we could have the probability of E and F, right? The and statement, probability that a selected high school student has never passed a stats class, and the probability and the event that that individual does not have a full-time job before the age of 20. So we can kind of mix that up into a word problem, and it makes it a little more difficult to dissect. So there are examples like that in the homework, so make sure you pay close attention to those so that you know how to write them down and how to tell them apart. Okay. One of the, I don't know, it's a benefit and at the same time the detriment to the MyStatLab is that when you're working on it, if you're confused, they do help you, right? I covered some of those help things, help me solve this, and some of the aids, some of the aid that's there for you. So that's really good, and it's good and useful. But make sure that you don't over rely on it, because when the test comes around, I expect you to be able to do these things on your own. So you'll have to read the word problem. You'll have to identify what the different events are, and the and statements versus the or statements. Okay. Any questions on this problem? No? 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 Okay, so here's what the author did. Probability of event E, there were 6 of them, 6 out of 36. Probability of event F, there were 10 of them, 10 out of 36. Probability of E and F, we said there were 3 of them, 3 out of 36. Okay. So then the probability of E or F is equal to the probability of E plus the probability of F minus the probability and F, which gives you 13 out of 36. And again, we could have also just counted, right? In this particular case, we had that benefit. One last concept in this section, which is complements. So let S denote the sample space of a probability experiment, and let E denote an event. The complement of E denoted with E with a little c in the top right-hand corner is all outcomes in the sample space S that are not outcomes in event E, right? A nice little picture of that is here. So remember, our giant rectangle represents our entire sample space, all possible outcomes, and then we can group up some of those simple events into a compound event, or it could be that capital E just represents a simple event, but at any rate, so here is some subset of the simple events that makes up a compound event. So event E is drawn this way. So everything not in E, everything outside of E, but inside our sample space is what we call the complement of E. Right? So it must be true, and I don't like seeing it this way myself. I like seeing it in this direction better. Well, okay, first of all, it must be true that the number of events in E plus the number of events in E complement must equal the number of events in our sample space, right? Like if we go back to our little example with the little ping pong balls. Here's event E. It's the 8 and the 9, for example. Everything else is out here in our sample space. Good. So if we call this event E is the 8 or the 9, then E complement would be everything outside of E. So E complement would be the number 0 or the number 1 or the number 2 or the number 3 or the number 4 or the number 5 or the number 6 or the number 7. Right? It's all the other ones that are outside of E. Good. Good. And E complement doesn't care about other events. So for example, there could be another event F over here that has the 2. That's okay. It doesn't care. And maybe, in fact, maybe the F also has an 8. So they have something in common. It doesn't matter. That doesn't change the results of E complement. Right? E complement is everything outside of E. And the 2 is still outside of E. The only thing inside E is the 8 or the 9. Good. So it must be true that all the number of outcomes in E plus all the number of outcomes in E complement must be equal to all the number of outcomes in our sample space. Good. It must also be true that the probability of E plus the probability of E complement, E complement, must be equal to 1. Right? If I go back over here to our little ping pong ball example, in every experiment, remember we have 10 little ping pong balls, 1 little ping pong ball is going to be selected, and either event E occurs or event E doesn't occur in every case, right? You're either a winner or you're not a winner. That's the way it is. The dealer either picked a 9 or an 8, right? So I'm either a winner because he picked one of the 2 balls I put money on, or I'm not a winner. He picked one of the other balls. Good. So the probability that I win plus the probability that I don't win has to be equal to 100%. One of those 2 things will happen. I will either win or I will not win. So I like to see it presented this way myself. But once you have it in this way, the probability of E plus the probability of E complement equals 1, then you can use a little bit of algebra and move things around. So you can say that either probability of E is equal to 1 minus the probability of E complement, like that. Right? I just subtracted this from both sides. Or I can subtract this from both sides and say that the probability of E complement is equal to 1 minus the probability of E, right? Which is what this is right here. Good. So this becomes beneficial for us when one probability is much easier to identify than the other. That sometimes happens in particular in our homework. You're going to be given cases where they might ask you to find probability of E, for example, and that might be a lot of work. That might involve counting a lot of things or adding a lot of numbers together. So it's possible, but just a lot of work. So you might be clever and think to yourself, wait a minute, if I instead think to myself, what is the complement? Maybe the complement is really easy to solve. Maybe the complement is just a very simple calculation. And if I can find the complement, then I can use this property, that 1 minus the probability of the complement equals the probability of E, to be able to get to my answer faster. Good. For example, according to the American Veterinary Medical Association, 31.6% of American households own a dog. What is the probability that a randomly selected household does not own a dog? Right? So own a dog and does not own a dog should be complements of each other. So I know that this must be equal to 1 minus the probability that we own a dog. Probability that one randomly selected household owns a dog, which is 1 minus 0.316. So this is equal to 0.684. Right? There's a 68.4% chance that they do not own a dog. Good. Okay, so this was one example of the application, but there are better examples. So you say this one. Here we have a table that describes travel times to work for residents of Hartford, Connecticut. Okay, so the frequency is the number of citizens of this county. So 24,358 of the citizens take less than 5 minutes travel time to go to work. It's pretty nice. 39,112 take between 5 to 9 minutes. 62,124 take between 10 to 15 minutes, and so on and so forth. So part A, what is the probability that a randomly selected resident has a travel time of 90 or more minutes? 90 or more minutes. Okay, well, in order to find a probability, we're going to have to figure out the sum of all of these. Okay, so that's the first thing. This is an example of empirical probability. Perhaps. I'm not really sure if this is every single citizen in the county, or if this is like a survey that they used and got our answer. It looks like it says a census, so it's supposed to be an account of everybody in the county. Okay, so it's an account of everybody in the county, so if it really is everybody in the county, then this would be classical probability. If it's just a random sampling of the people in the county, then this would be an empirical probability. Okay, so we need to add all these numbers up, and I think that they probably did this already. Let's see what that is. Oh, okay, here we go. So this is indicating, I already know, there's a total of, and if we add all of these numbers, that's what this denominator is. So 393,186. 393,186. Okay, so we can just take our calculator out and add all these to confirm it, but I'm just going to assume that that's the case. Okay, So the probability that one randomly selected citizen travels 90 or more minutes, that's these guys right here. So this is a pretty simple statement. The probability of, and then I'm going to write down the event, 90 or more, That's good enough notation to know that it means that, right? Equals to, well, it's the number of people that qualify under that. That's the 4,895 divided by everybody. So 393,186. Right? That's the fraction that will give us this probability. Good. And then we can convert that into a decimal, and we get this, 0.012. Good. Okay, now part B says, compute the probability that a randomly selected resident of the count fort will have a commute of less than 90 minutes. Probability that it's less than 90 minutes, well, that's all of these other people in here. Right? It counts people that have less than 5 minutes, people that have between 5 and 9, people that have between 10 and 14. So if I wanted to compute it sort of in a straightforward way, I would have a lot of things that I'd have to add. Right? So this is equal to the probability that it's less than 5, plus the probability that it's between 5 to 9, plus the probability that it's between 10 to 14, plus right? And you can see that's going to be a lot of different probabilities that I'm going to have to compute. Good. Luckily, these are all disjoint, so it's not as complicated a formula. Just have to find the probability of each one and then add them together. Right? It's clear that these are all disjoint, right? Because when you randomly select one person, they can't give you both answers. One randomly selected person, you figure out what their commute time to work is. They can't say that their commute time is between 5 to 9 minutes and at the same time it's between 45 to 59. Now, maybe there might be some ambiguity there. You're going to have to define exactly what you mean by a commute time. In a particular day, there might be a day when it takes a long time. There was an accident or something, so it might take them longer some days versus others. There might be a case where their office varies. Maybe they have an office downtown, but they also have an office someplace else. So some days he goes to one office, some days he goes to another office. So it can get a little more complicated. But assuming we clear out all those kinks, it should be the case that each person is assigned to one of these little boxes. Right? Otherwise, they would be counted here, and they would also be counted over here, and then that would mess up the whole thing. Right? We're assuming each person is counted only once, and they, are identified as one of these things here. Okay, well that's a lot of work, right? So instead, we want to use the complement rule. We want to note that the probability that someone takes 90 or more, probability that someone takes 90 or more, plus the probability that someone takes less than 90, these two must add up to 1, right? These are complements of each other. Absolutely everybody will either say 90 or more, or they will say less than 90, right? These two things are complements of each other. And so we wanted this one, so we can say that the probability that it's less than 90 is equal to 1 minus the probability that it's 90 or more. Good. Okay, so we already had this one. This one is equal to 0.0012, I think it was. That's this. In fact, I should copy it down, fraction. So this is equal to 4895 divided by 393,186, which is 1 minus 0.0012. Good. Questions?
I think you put an extra 0.
Oh, thank you. Yes, good catch. 0, 1, 2. Okay, so this is 1.2%. So this should be 98.8%. 0.9, 98.8%. 98.8%. Good. Thank you for catching that. Any other comments, questions? Okay, so the probability that's less than 90 is equal to 1 minus the probability that's 90 or more. So that's why we can simplify our work this way. Otherwise, we'd have to do a whole bunch of more calculations. Questions on anything? Questions on anything? Okay, what time is it right now? 5, wow. Okay, boy. Let's... Let's get started on a handout. More fun with the same ideas. So no new concepts here, it's just reinforcing all the same things we've been learning in sections 5.1 and 5.2. Okay, so here's some examples of experiments, some classic examples that we'll get to look at, or we work with a lot. Rolling a 6-sided die, for example, this is a very classic example of an experiment. And then here is our sample space. Right, 1, 2, 3, 4, 5, 6. Oh, I missed the first one. Experiment could be as simple as flipping a coin. So the sample space is just heads or tails. Good. An example of an event, in this case a simple event, is just to say what's the probability that it's heads, and that's going to be really easy. Right? I'm just going to draw it right over here. So the probability that we get a, ooh, I don't want to do red. Erase, go over here. There. So the probability that we have heads, just put an H, is equal to 1 out of 2, right? Because there's only 2 options. Good. Okay, rolling a 6-sided die, the probability that we roll a 4, again, that's a simple event, and that's just going to be 1 out of 6, right? So probability, let's put a 1 here. Probability that we, the die equals a 6, oops, sorry, not a 6, equals a 4, is equal to 1 out of 6. The probability that we roll a number that's less than 5 is strictly less than 5, so that would be a 1 or a 2 or a 3 or a 4. 5 does not count as less than 5. So the probability that the die is less than 5 equals 4 out of 6. The probability that we roll an odd number, so that would be the 1, the 3, the 5. 1, 3, 5. Right? So the probability that the die equals odd is equal to 3 out of 6, or 50%. Okay. The probability that we roll a multiple of 3, right? 3, 6, 9, 12, these are multiples of 3. So multiple of 3 that would work here is just a 3 or a 6. Those are multiples of 3 that we can roll. So let me just write that. Probability that the die equals a multiple of 3. Multiple of 3. That would be 2 out of 6. Good. And we can always go back with our calculator and convert these into decimals. Good. Okay, so now if we roll a pair of dice, we've seen this before. Here's our sample space, all possible outcomes when two six-sided dice are rolled. And then we can combine our knowledge from before to find some of these things. What's the probability that we roll a pair of dice where both numbers are even? Probability that we roll, and then the pair equals even numbers. Even numbers. Well, then we'd have to count, right? So let's start highlighting things here and counting. So we want a pair where both numbers are even. Well, that knocks out all of this whole column, because they're all ones. And it knocks out this column and this column, right? Okay, so both are even is going to be like that one and that one and that one. Okay? And then we knock out this whole column, and it could be kind of like that one, or 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 that one. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9 ways that it can happen. Good. So 9 out of 36. Good. Okay, can I erase the highlighter? Okay, let's do the next one. What's the probability that we roll a pair where the sum is sum of the two is 7? The sum equals to 7. 6. Probability that the sum equals 7. Equals 7. Okay, so again, let's highlight. Equals to 7. So that would be this guy, or this one, or this one, or this one, or this one, or this one. So it's this little diagonal here. That's all the ways in which the sum equals to 7. And there are 6 of them. 1, 2, 3, 4, 5, 6. So this is 6 out of 36. Good. All right. Roll a pair where both numbers are the same. Okay, both numbers are the same. So like this one, 1, 1. Or 2, 2, or 3, 3, or 4, 4, or 5, 5, or 6, 6. So it's this diagonal in the other direction. So again, there are 6 of them. So number 7 here. This is probability that we roll a pair where both numbers are the same. Both numbers are same. Again, it's 6 out of 36, right? This diagonal here. So really, the classical way really boils down to counting things. We've got to be able to count the number of ways that something has happened. Okay, moving on. Here's another classic example. We have a 52 card deck. Right? If you're not familiar with it, we have 4 different suits. We got spades, hearts, diamonds, and clubs. Right? And then we have aces, which double as a 1. Sometimes the ace in certain games is considered like a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And sometimes the ace is considered to be over here on top of the king. So we have jacks, queens, kings. And in some games, the ace is bigger and it appears over here. In some games, they kind of lap around. You can go from jack, queen, king, ace, 2, 3, 4, 5. And in some games, you can. So it depends on the game. But there are 13 cards total in each suit. And there are 4 suits, so there are 52 cards. Good. So what's the probability that we choose a club? Right here. Probability that one card is selected and it's a club. Well, that's these guys. So again, we're counting. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There are 13 different clubs. So this would be 13 out of 52. Good. Probability that we choose a 5. Oops. 9. Probability that one card is selected and we choose a 5. Okay, so let's highlight all the cards that are 5. So that would be this one, the 5 of clubs, the 5 of diamonds, the 5 of hearts, or the 5 of spades. there are 4 different cards that satisfy that statement. So 4 out of 52. Number 10, choosing a face card. Okay, so obviously all the cards that have a face on them are considered face cards. So that would be these guys. Okay, these all have a face. The king, the queen, the jack, they all have faces. The ace does not have a face on it, so that's not considered a face card. The probability that we get a face card, well, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different cards in the deck that have a face card. So it's 12 out of 52. And then the next one, choose a red ace. A red ace. Already that it's a red ace. Red ace. Well, again, let's highlight those. How many aces are red aces? Well, that would just be this one and this one, right? There's only 2 red aces. So that would be 2 out of 52. Any questions about any of these? I'm kind of going through them, but I feel like at this point we should be pretty happy with the classical way of finding probabilities, especially when a nice Venn diagram or a nice presentation is given. Good. So, this reinforces our understanding. The probability of event E is equal to the number of ways event E occurs divided by its sample space. So if we have a simple experiment like flipping a coin, we just count things. So the probability that if event E is defined to be the probability that we flip one coin we get a heads, then it's equal to 1 out of 2 or 50%. Good. If we roll a 9-sided die, let's kind of complicate things. This is what a 9-sided die would look like if you've never seen one. If we roll one 9-sided die, what's the probability that we roll a roll of 4? Event E is that we roll a 4. What's the probability we roll a 4? Well, there's 1 out of 9 ways to do that, which turns into 11.1% chance. So if we had 2 9-sided dice, oh, sorry, I jumped the gun here. Okay, so in that space of having a 9-sided die, what's the probability that we roll a number that's less than 5? So less than 5 includes the number 1, the number 2, the number 3, the number 4. Right, so there are 4 ways to roll a number that's less than 9. Our sample space is 9. So the probability is going to be equal to 4/9. Good. Probability that we roll an odd number, well, we could roll a 1 or a 3 or a 5 or a 7 or a 9. It's a 9-sided die, so there's 1, 2, 3, 4, 5 different options. Sample space is still 9 or 5 out of 9. Or the probability that we roll a multiple of 3. Okay, multiples of 3 are 3, 6, 9, 12, 15, so on and so forth. But it's only a 9-sided die, so we can either roll one of these guys to satisfy that statement. There's 3 ways that can happen. Still 9, so there are 3 out of 9 ways that can happen. Any questions? No? Okay. Okay, so now a much bigger sample space. What if we roll 2 9-sided dice? So let's fill out the table of all things that can happen. So going this way is all the cases where the second die is a 1. So this is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so then going this way, we go 2, 3, 4, 5, 6, 7, 8, 9. So all of these have a 1. First one's always a 1. First one's always a 2. First one's always a 3. A 3. 4, 4, 5, 5, 5. So of course if we didn't have Corona, you'd be sitting in a classroom filling this out yourself, as you might have guessed. 8, 9, 9. Okay, and then going this way, this is all the cases where the second one is a 2. So I always put a 2 there, 2 there, 2 there, 2 there, 1 there, 3, 3, 3, 3, 3, 4, 4, 4, 5, 5, 6, 7, 8, 9, 9, 9. Okay, so filled it all out. Here is, oops, nope, missed one. So here is a table that shows all possible outcomes when two 9-sided dice are rolled. And again, we could do the same as before, count things to find probabilities. So now we can use this table to answer these guys. What is the probability to roll a pair where both numbers are even? Okay, so a pair of 9-sided die and both are even. So again, we go back to counting things. Both are even. Both are even, well, that completely eliminates this group here. So it's going to be this one, or 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 this one, right? Or this one, or this one, or this one, or this one, or that one, or that one, or that one, or that one, right? So all those highlighted ones are the ones that are going to satisfy that statement. And there are 1, 2, 3, 4 here. So there's 4 of them from here, and 1, 2, 3, 4 of them from there, and 4 of them from here, and 4 of them from there. So it's 4, 8, 12, 16. There are 16 ways that can happen. Good. So there are 16 ways. And how many are there total? There are a total of 81 in our sample space. There are 9 going this way, and there are 9 going this way, so there's a total of 81 in our sample space. 81 outcomes. Oh, so I should say n of s equals 81. Good. So the probability that the pair, both pairs are even is 16 out of 81. Good. Good. Okay, so now let me erase these guys. So that. Okay, so then the next one is, what is the probability that a pair, the sum of the two is 7? So roll a pair where the sum of the two is 7. They have to add up to 7. Okay, so let's highlight all the ones where they add up to 7. So these added up to 7, and then these add up to 7, and then these add up to 7, and these add up to 7, and these add up to 7, and these add up to 7. That's 1, 2, 3, 4, 5, 6 different ways that the two 9-sided dice can add up to 7. Good. No other way that can happen. Not exactly, that if they have to add up to exactly 7. So 1, 2, 3, 4, 5, 6 different ways that can happen. So 6 out of 81, or 6 over 81. Good. Where both numbers are the same. Both numbers are the same. Let's highlight a different one. Both numbers are the same. Well, that would be this one, and 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 this one. So there's a total of 9 different ways that can happen. 9. So 9, still 81, or 9 out of 81. Roll a pair where the sum is equal to or greater than 10. Equal to or greater than 10. Well, that's a lot of them, isn't it? A lot of them are equal to or greater than 10. So let's go back to highlighter. Well, clearly these guys, those are equal to or greater than 10. Equal to or greater than 10. This one fails, but this one doesn't. Okay, all of these guys. All of these guys. Equal to or greater than 10. Equal to or greater than 10 is all of these guys, including that guy. And then that one fails, so this is going to be 10. So it's going to end up looking like this giant triangle over here, where we don't include that one, we don't include that one, we don't include that one, we don't include that one. Let's get rid of all of these guys. So it's these. Good. So we can count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45. 45 different ways that can happen. Equal to or greater than 10. 45 out of 81 options. Almost done, 2 to go. Roll a pair where the product is even. Okay, roll a pair where the product is even. So let me erase this. The product means the multiplication, right? The multiplication is even. So if you want to go back over here, let's go over here. 1 times 1 is 1, that fails. 1 times 2 is 2, that'll be even. 1 times 3, that's 3, that's not going to be even. 1 times 4, okay, so I want all the ones that have an even one in them, like that. Okay, now 2 times anything is going to be even, so that's just going to be everything here, right? 2 times 3, 2 times 4, 2 times 8. Anything that has a 2 in it is automatically going to result in an even product. And, well, over here the 4 is the same thing because 4 is even. 4 times anything is also going to be even. So that's going to include all of the ones that have a 4 in them. And then same thing with all the ones that already have a 6 or an 8. So all of these are going to result in an even product. And then over here, 2 times 3, right? At least one of the 2 has to be even. So that one's even, that one's even, that one's going to be even, that one's going to be even. Good. Over here, this one and this one and this one and this one. And then we start to see a pattern with this table of which ones will work. Right? So if 2 numbers are going to be multiplied and in order for the answer to be even, at least one of the 2 numbers has to be even. Right? Maybe both are even, but at least one of them has to be even. Good. So now we just have to count 1, 2, 3, 4, 5, 6, 7. Okay. Well, these are all of them, right? So these columns are 9. Let's just make these. These are all 9 of them. All 9. All 9. All 9. And there's 4, that makes it 36, right? 9, 18, 27, 36, 36. And then these are all 4s, right? 1, 2, 3, 4 of them here. 1, 2, 3, 4 of them there. So it's 4 there, 4 there, 4 there, 4 there, and 4 there. 1, 2, 3, 4, 5 columns where there are 4, so that should be 20. So if I add all of these up, I get 20 plus 36, or 56. Okay, if you followed that, great. Otherwise, you could just count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Right, count them all, and hopefully you'll get to 56. 56 over 81, 56 over 81. And finally, the last one, roll a pair where their difference is negative, and you subtract them in this order, die 1 minus die 2. So in order for the difference to be negative, if we're doing it in this order, it must be the case that this one is small, or smaller, than this one. This one must be the larger, right? Like 3 minus 5, for example, will result in a -2. That's what we're looking for. All the cases where the first die is smaller than the larger die. It's going to be a lot of stuff. Let's erase everything from here. Fortunately, it erases all the underlying values too. All the cases where die number 1 is strictly smaller than die number 2. So going back to filling out these things, this should be a 2, 3, 4, 5, 6, 7, 8, 9, 1, which means all of these should be 1s, 1, 1, and all of these should be 2s, 2, 2, 2, 2, 2, and then 3, 3, 3, and then 4, 4, 4, 4, 4. 5, 5, 5, 6, 6, 6, 7, 8, 9, 9. Okay, so going this way should be a 2, a 2, a 2, a 3, a 4, a 4, a 4, 5, 5, 6, 7, 8, 9, 9. Okay, that's about all of them. Okay, so all the cases where die number 1 is definitely smaller than die number 2. So here this works. 1 minus 2, that's going to be negative. And this one and this one. Okay, well, once we get to that point, then all of these will work. Good. Here it doesn't work out. Here it doesn't work. Here it is. 1 is less than 2. Okay, so all of these guys are part of it. And this one's and this one. So it ends up being this little triangle that starts to get formed. These ones, and these ones, and these ones, and this one. Right? So if you think about the column where they were both equal to each other, 1, 1, 2, 2, 3, 3, right? It's the one, the triangle that's formed below it is going to be the answer. So there's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36 ways that this can happen. Good. So let's come back over here. We'll put 36, still 81. So 36 out of 81 ways that can happen. Good. Okay, so moral of the story here. In some cases, we're able to completely spell out what our sample space is, and then finding probabilities really just comes down to counting things. Count experiment. Count how many of those satisfy the compound event, and then you can create your probability that way. Good. All right, this is a good place to stop. We'll come back tomorrow, and we'll continue with this other example about the random babies. So you should be able to do all of the homework from 5.1 and 5.2 at this point. So you guys should be all at least in 5.2. Moving forward, don't wait for me. Start reading the next section and doing what you can as we cover it. Maybe I get to it eventually, and we'll get to your questions and issues. But you should at least try it on your own, because there's a lot of work, and it's going to be very easy to get lost in the middle of it all. Okay, so if you're right now in this meeting, or if you're out there watching on YouTube, make sure you create an account and get started on your homework. There's about a little bit more than half of you guys have already opened an account and gotten started, but there's a big group of you guys that have not opened an account and gotten started on your homework. So please do that today. If you don't know how to do that, make sure you look at the previous videos on there to help you register. Any questions on anything? No questions, no questions, no questions. All right, then I'll see you tomorrow then. Have a great day.